All right, here we go. So on exercise one, this example, again, I'm trying to show you as many things as I can. No one word problem is done the same. So therefore, give you the examples that you need to work them out. So on this one here, it says a motorized robot moves across a coordinate plane. Its position is written as x, t, y, t. Remember, those are your parametric equations. That's all it's saying. At time t seconds is given by this equation here. So again, this is the parametric equation. X of t would equal whatever the x point is plus t times whatever the x velocity is, or not the velocity, sorry, vector. And then it gives you what a is. Remember, a represents that first point. So this is where the x is starting. This is where the y is starting. The vector is like your slope. This is how the x is changing. So it's changing by left 4, and that's what the y is changing. So it's like up 3. Right? Do we all understand the meanings of these still? So that hasn't changed since lesson 20. Yep. Slope. So this is like your slope, and this is like your starting point. In a sense, when you think of it as the y equals mx plus b, the v would be the m, the a would be the b. However, this is not meaning the y-intercept. It just means like a point in space on that line. All right, so then the units of distance are measured in meters. Again, dealing with word problems, it has to give you some type of units. All right, first question it's asking is where is the robot at time t equals 0? So to do this, all you got to do is just plug in your information. So we get, so it's x of t, y of t equals 4, negative 10. Again, all I'm doing is replacing things. Plus, I'm going to put the t on the right side, just looks better. Negative 4 and 3, so that's my v. And then my t, it told me t equals 0, so it's going to be times 0. Before I do any math, questions? Plus, yes. So this is my a plus my v and my t. I just literally plugged in everything it gave me. So we're good? Well, I did. I plugged the t in for 0. Well, because we don't know that. It's going to be the equation. So in this case, when we plug it in, think of it like this. You're technically doing this. You're figuring out what's the x value at time 0, what's the y value at time 0. That's it, because a scalar multiplied will multiply to both of this. This will pretty much zero out. And then when I add it, I would just get 4, negative 10. Pretty good? All right. Go ahead. So at 0 seconds past, this robot is located at 4, negative 10. So wherever you're imagining your plane to be, you have some center of the room. Your robot on this coordinate plane is 4 to the right, 10 down. That's where robot is. Go ahead. I think my maintenance crew would really hate me if I paint it. Maybe tape. Tape, yeah. Painter's tape, though, because it doesn't do the sticky. Any other tape leaves it sticky, and then they'll hate me still. Hmm. Yeah, 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 yeah. They'll definitely be mad about that. All right, part B just simply wants to plot this path. So again, we now know where robot is. Robot starts at 4, negative 10. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Give or take right here. All right. How do I find where the robot is after 1 second? Okay, let's do that. Exactly. That was the other alternative. So I could do this, which is x of 1, y of 1. Basically, we're going to figure out where the robot has landed after 1 second. When I multiply by 1, is it really going to change that vector? No. So I can just straight up add here. What's 4 plus negative 4? 0. What's negative 10 plus 3? Negative 7. Very good. So that means I'm going to now be 7 right here. Now, there's an alternative way to do this as well. Since we know the vector kind of represents my slope, and the first number is my change of x, and my second number is my change in y. From this point, I could just go left 4. So that would take me here. And then I could go up 3, which will put me there. So you could work it out using the formula or just realize that your vector is going to give you a slope. So let's do another one with using the slope application. So from here, I'm going to go left 4. So that's 1, 2, 3, 4. And then I'm going to go up 3. So 1, 2, 3 puts me about right there. And again, if you were to plug in 2 to represent 2 seconds, you would come out with -4, -4, right? Any questions on how to plot either direction? So you can, again, plug in an equation or just know what your vector means. So I'm going to kind of do my best job here. So this is the path of your robot. Why did I not add an arrow to the right? It's where it started. We don't have negative time, right? I can't go backwards in time. Not yet anyways. Or at least I haven't invented it because I didn't come back to tell me. Or maybe I'm not doing it on purpose so that maybe I don't need to know so that I work hard to find out the time. Yeah. There you go. It's like a timeline, right? So any questions on that? All righty. So now let's take that. We're going to answer some questions that go with it. So in part C, describe the path of the robot. When you see a question like this, it's asking for an equation of y equals mx plus b. Exactly. So that's actually what last period said as well. There's like, it went that way. That's great. I need more than just that way. So yeah, so to do that, to describe it, we're just going to give it an equation. So a couple things to note. When given a vector, remember it's labeled as your a and b, and the slope is b over a. Okay. And also remember that the b represents the y-intercept. All right, so knowing what we know, what was the vector again? Thank you, -4, 3. So therefore, what would my slope be? Good, 3, -4, very specific. So the vector is given to you as AB, but the slope atmosphere is B over A. Because the slope you're always taught is the change in Y over the change in X. We graphed it and go ahead. You're good. You're good. Oh, it doesn't matter. The negative can go on top or the bottom. When I teach linear equations for the first time to somebody and we're talking about graphing, I usually always say apply the negative to the numerator so that you either start by going up or down and then always to the right. But correct. So really here, it doesn't matter if you apply the negative to the top, the bottom, or just put the negative in the middle. All of those would be acceptable answers. I just left it with the negative here because it was with the negative there, but it really doesn't matter. But that's a very good question. All right, so again, we did it by algebra and we did it by graphing. What did the y-intercept end up being? Good, so we need that -7. So with the work that we've already done, we already know our m and b, so we don't gotta like do a whole bunch of math. We can draw out our equation. Go ahead. We only have to multiply by 1 to find y-intercept. So what if it doesn't like give you a nice clean number? Then you would have to use that concept of taking a point and the slope, plugging it in here, and go solve for b. So yeah, so I could have graphed it. Maybe my b was -7.1. What I would then have to do, so this is like worst case scenario, take a point. So whatever point you had, I think what was our original point? What was a? Or -10. So I would take this point and I would say, all right, -10 represents my y. My m, I still can get from my vector, so that's still going to be 3, -4. And then my x was 4 plus b. Now I can go calculate it by hand. So then like -3/4 would be -3, -10 plus b. then you would add 3. So then you would get -7 equals b. So yeah, if we, let's say the question didn't ask me to graph or find out what t times equals 0, and it just simply asked, hey, can you describe the equation? I would probably go this route just so I could go get my b anyways. Yes, ma'am. All right. This was as a stretching or question? Okay. So on part D, where is the robot 10 seconds after it starts moving, and how would I figure that out? Perfect. Exactly like we did on part A when we plug in 0 in for T and 1 in for T. Now I can plug in 10. The alternative is I could move the robot 10 times to figure out where I end up, but it's a lot easier just to plug into the equation. So remember, this is going to be x of 10, y of 10, because now I'm looking for 10 seconds. My A was 4, -10, plus my B was -4, 3, and this time my T is 10. Before I actually do the math, Jacob, are you good? Yeah. Any questions on how those numbers came to be? I just plugged it into the equation it gave me on the very beginning of this part. It's good. All right, so then we just do math. 4 plus -4 times 10. What's -4 times 10? -40 plus 4. -36. Very good. So multiplication before addition. So I have to multiply this scalar first. So, okay, this is not a fraction. Let me rewrite it. So this is the vector form. If I wrote it as the parametric form, this is how it look. So the scalar here would go to both of these numbers, and then now I can calculate my x. So when I did that, -40 plus 4 gives me that -36 here. So again, on this one, 3 times 10 would be 30 plus -10, 20. So that means that the robot after 10 seconds would be left of the origin by 36 spots and then up 20 spots. Actually, I guess 30 left 36 meters, up 20 meters, since it did give us the meters earlier. Questions? I don't know. No, it's not a rate. I think it says distance. Caleb corrected me on that one yesterday. So yeah, definitely. Yeah, this is just going to be distance. But you can use vectors with velocity as well. So I think it's where I'm getting tricked up, because you can do both. So any questions on D? Were y'all pretty excited to go talk to Mr. White and be like, hey, we learn about vectors and all this stuff? Oh, usually I run into them and I'll let them know what we're doing. Today, yeah. Oh, band's over?
Yes, sir.
Good. Welcome to class. Missed you yesterday and today. All right, so in part E, it says, where's the robot when it is 10 meters from where it started? So what is the 10 meters going to represent in total? The distance, right? So I'm just going to run, I'm just going to give you like a sketch here. So here's where my original dot was. I want to know at what time am I 10 meters away? All right. So to do that, I kind of need to find out what the distance of the vector is to begin with. So what we can do is, since I'm going to kind of use part B. On part B, yeah. So on this one, I'm going to try to do a rough sketch. Y'all good? All right. So if this is my point, you already have this on B. I'm just kind of trying to redraw it. And I'm right here. I saw that I went over 4, right? Because I went left 4. And then 1, 2, 1, 2. I went up 3, right? So I'm trying to find the distance of this vector. How would I do that? The square root, perfect. So moral of this story, so you don't have to keep like drawing these figures out. If you're given v, which was -4, 3, this is the same thing again as your a and b. And when I'm looking for the distance to begin with, remember that's going to be the square root of a squared plus b squared. So you can either draw it out so that you see that you're producing the hypotenuse. Yes, ma'am. Oh, and then, or you could just realize that when given the vector, I could just do -4 squared plus 3 squared. What's -4 squared? 16, good. And what's 3 squared? 9. 16 plus 9, 25. And the square root of 25 is 5. Very good. So what we just found is that the distance for 1 second was 5 meters. I'm looking for 10 meters, so I just have to do the next point. So I'm going to go left, 1, 2, 3, 4, and then up. Yeah, he's going at 5 meters per second. Yeah, for sure. So this would be another 5 meters. So where's that location? You probably have a better graph on B. If you don't know, if like you're me and you have a bad drawing, you know it's 2 seconds long, right? You can plug it into the equation. Perfect. But again, let's say you have a bad drawing, you're just not a good drawer. You do realize it needs to be 2 seconds. Then we can just plug it into that equation. So x of 2, y of 2 would equal my a, which was 4, -10, plus my vector, which was -4, 3, and then I do 2. So again, so let's say again, you just didn't know that drawing. -4 times 2 would give me, and then -8 plus 4 would give me -4. 2 times 3 is 6 plus -10 gives me -4. So again, if you have a great drawing, you would have saw it landed at -4, -4. But if you're like me, poor drawing, but you know it's going to make it 2 seconds to get 10 meters away, you can do it that way as well. We good with this? Yeah. 5 meters. Side note, has nothing to do with this problem. 5 meters, 1 second. Oh, I have no idea. How many meters are in a mile? 40-meter dash would be, there's 400 meters, right, in one lap around the track. So that's 1,600 meters in 1 mile. Okay. 1,600 meters, 1 mile. Mile. I don't need an equal sign, actually. Yeah. Seconds, and we need to do this miles per hour. So that would be 60 seconds in a minute, 60 minutes an hour. So 3,600 seconds in an hour. So this would then, the meter would cancel with meter, second would cancel with second. I'd be left with miles per hour. So I'm not doing this math, but you can do 5 times 3,600, divide it by 1,600. He asked a question. I answered the question. 5 times 3,600. What's that? 72, 14, 4, 18,000. is what 5 times 3600 is. So 18,000 divided by 1600. Oh, it's going to be 1600 goes into 18,000. It's the same question as 180 divided by 16. So that's going to be 1 here over the 2. That's 11. 11.4 would be 1/4. So 11.25. Are you just saying that to say it?
Oh, check.
Yeah. So 11.25 miles per hour is how fast the robot's going. Has nothing to do with this problem, just an FYI. But that was a great question. So he's not, I mean, he's traveling fast, but he is a robot. Okay. Back to the regular programming. On part F, is the robot traveling at a constant speed? Yes. He is traveling at 5 meters per second or 11.25 miles per hour. Huh? 10 meters per 2 seconds, which is the same thing as 5 meters per 1 second. Or if you want to get real technical, it's 20 meters per 4 seconds. Insane concept. So, so this is a yes, not just a Y. Sorry, let me finish this thought in my head. Is meters just M? Yeah. Sorry. So yes, it is traveling at 5 meters per second or 11.25 miles per hour. Questions on this type of word problem? Yes. All right, so let's do another type of these problems. Try and give you as many examples as I can give you. Yes, ma'am. That's fine. So I did tell you that sometimes it does not give you a graph. So graphs do make it a little bit easier. So this does not give us a graph. So we're going to need to draw out some things or just assume some things that always happen. Let's go based off what we did in the first 2 examples from yesterday. By the way, that is already in Google Classroom. I did that this morning. All right. So part 2 says a rowboat is crossing a river that is 500 meters wide. I'm going to kind of, here's a river. I'm going to call this a river that's 500 meters. 500 meters. And then it says, all right, here's my little rowboat. All right, there's my little rowboat. Maybe it's a sailboat. I don't know. But he is traveling at a speed of due east. What do we know when we see the word due? Straight. It has a 90-degree angle. So due east would be straight this way at 2.2 meters per second. I have no idea if that's fast. No, it's going to be about 5 to 6 miles per hour. That seems pretty fast for a rower. How fast do we normally walk? Does anyone know? I think we walk 5 miles an hour. I got people like on the highway that be just traveling at like 30 and it feels like we're not moving. I don't know. Maybe. Well, I have no idea. Anyone know? Yeah. There you go. So maybe he's traveling a little bit. Then it says the river's current is due south. So again, we see that word. Thank you. So again, we see that word due. So that means it's going to be a direct 90-degree angle. So we don't got to worry about these changes. Oh, I really don't know how it's. Oh. Okay. I don't know. I just added it here mainly because I was like, all right, if we're traveling at this speed, and we have a current coming this speed, I can determine that my boat is going to be traveling in this direction. Most vectors are. It definitely is. So I just added to this point because I know I'm traveling at this speed. I'm being pushed at this speed. So really and truly, I'm going at some type of angle. We are trying to calculate what is that angle and what is our distance to travel. We can't assume. So it definitely looks like a 45-degree angle, but we cannot assume it could be a 44-degree angle, right? So we're not going to assume anything, or 46, right? We just want to know what is the resultant velocity of this boat. So then this is where I get confused because I know vectors as velocity as well. So it can do by measurement here, but this is the same concept. If I want to know what my speed that I'm traveling at this angle, what could I do to find that out, to find the missing side? The square root of a squared plus b squared. So in this case, the square root of 2.2 squared plus 0.8 squared. Right, if we don't know, we do know that this and this is a 90-degree angle. So with Pythagorean theorem, I can then say to find this one, that's a squared, the square root of a squared plus b squared. Do on both of them. If it did not, and it said like northeast of what we saw yesterday, then we got to do the math where we got to find point P, find point Q, find the displacement of it, and then use that point to help us find out where we're at. So what do we get here? Something. I don't think 2.2 is 4.4. Is it really? That 84. Yeah, because if I say 22 squared is 44. 64. 22 squared is 484. So because of the 0.2, 2 decimals move it to the left. My bad, 484. All right, then 4.84 plus 0.64 gives me. And then the square root of that. 2.34 meters per second. So that means you are rowing at 2.2 miles per second. The current is pushing you at 0.8 per second, but that means now your speed in the angle that you're going, you're actually traveling at 2.34 meters per second. So the current is kind of helping you get there a little bit faster. Yeah, we're going more southeast now. All right, so it does ask for the resultant. So that means that it needs the speed or the distance, and then it also needs our angle. What angle are we actually going at? So let's determine that if it's 45 degrees. How do I find the angle? There it is, tan inverse of B over A. So in this case, that's tan inverse of 0.8 over 2.2. Your y, your change in your y will always be your B. So think of it like this. This right here is your change in your y, and then this is your change in your x. So this is my x-axis. This is my y-axis. Go ahead with the question. We brought it back yesterday. And I think we brought it back last Thursday too, actually. We had brought back theta and the square root, I think, since lesson 20. And then we skipped lesson 20. Oh, lesson 21 with the stone bridge. Oh, my knee just gave out. Oh, don't get old, guys. Stay young forever. That's age. That's right. Yeah. All right. Okay. Let's try that again. What's the tan inverse of 0.8 divided by 2.2? Are we in degrees? Radians? Radians. Make sure you're in degrees. 19.9? 19.8? Looks to me like 20. Okay. So this is actually a 20-degree angle. You never seen the squiggly things? No, this is not an equal sign. This is an approximate. An equal sign would mean this is equal to this. The squiggly line says this is approximately this. So yeah, I've never seen that. Gotcha. Yeah, close enough is literally what it means. Yeah, we're approximately this. We're happy here. So not 45 degrees. So it's actually a 20-degree angle that we are progressing. So it most likely is because the current is not as strong as how fast we are traveling. If we would have seen that the current and us are the same, you would have then known that it was 45 degrees. So both the current and you have to be traveling the same speed. Questions on how to use what we've been doing, but in an application form. Okay, let's do some more then. Part B then says, how long does it take for the boat to cross the river? Well, I am traveling 2.2 meters per second, correct? So if I want to know how long that's going to take me to go across, how far is the river? 500. So how many seconds will it take me to go from 500 meters across at going 2.2 miles per hour? We're going to account for it. We're just not quite there yet. So right now we're just going to see if we did not have any current, what would the measurement be? That great. So without current, it would take us 227.273 seconds to get across. Roughly 3 minutes and 47 seconds. It's not too bad. What's 500 meters? Is that like a football field? What's No. It's 400 meters for an entire loop. So, yeah, maybe. I don't know. Because you got to account for like the end zone and the other extra part. I don't know. You ever done bear crawls and count at the meters as you're like, doing your bear crawls? There is a meter stick. There's 3 feet in a meter, right? Oh, I don't know the answer to that. A meter stick is the same thing as a yardstick. So a yardstick is 3 feet. So there's 3 feet in 1 meter. So there's 1 meter in 1 yard. 1 meter equals 1 yard. So 100 yards would be 100 meters, give or take. That's my assumption. Ain't that what they call it? A meter stick, yardstick, but they're the same size? Yeah. Okay, there you go. I don't know that measurement. Roughly, I would have said, a 5 football fields. Yeah, you're right. Who said that earlier? Yeah, you're right. 5 football fields. Okay. So 3 minutes and 47 seconds. Not too bad time. All right. The issue is we do have a current. So we got to determine how far is that taking me off course. So what you do is you take this number and multiply it by 0.8. This will take you to how far you just traveled here. 0.8. To account for the current being affected to you. So this is going to be our 0.8 with our time. And where's that put us? 181.81. All right. Meters. So he was basically to travel 500 meters. He also traveled, this right here would have been 181.81 meters. So that's how far off he was. So if he was just trying to go straight across to meet somebody, he would have been a little off. Almost 2 football fields off. Go ahead. The distance here, I think that's what we're getting into in part D. I guess not. Yeah, I don't know. That would be a Whiting question. But just trying to find the distance here, I know this is going to be 500. So the time it would take is going to be 227 seconds. And then the fact that we're this far off with the current, it's going to take us 181.81 meters off course. So if you wanted to find the distance there, we could do 500 squared plus 181.81 meters squared. Yes. What is this answer here, though? I bet this will be What is this one? 500 squared plus 181.81 squared. Okay. What is this one? What is this? Really? Should be more than 500. Maybe it's not. Maybe it's not. Maybe it's 280. Is it 283? Okay, that makes more sense. Okay, so I'm about to say, I think it has to be more than 500. So 532, what? 02. So really, this guy traveled 532 meters from this point to this point to account for that current. So there you go. All right, so we got 2 minutes. Great. Let's do number 3. Number 3 has 1 part. 4 has 5 parts. Yes. Let's look at this. All right. So it says, consider the airplane from the example that we saw from the other one from the example that leaves Dallas Fort Worth and goes to Atlanta. Had a bearing of 50 degrees. Note that the bearing is the number of degrees east of north. The plane is then traveling at a speed of 550 miles per hour. There is now a crosswind of 40 miles per hour due east. What is the resultant velocity of this airplane? So again, well, you can just use the regular drawing, but let's pretend that Dallas Fort Worth is our origin. Okay, let's say that's the center of our space. It has a bearing of 50 degrees. We saw that that means that this would be 50 degrees. So that would mean that this is 40 degrees. What it's adding, it's now saying, all right, this plane is now being hit with a 40 mile per hour due east. That's due east, so that's directly. So that means we have, I'm going to write it here. I don't really know where it's going to take me, but this is 40 mile per hours due east. This was again 550 miles per hour. All right, so we got a good setup. So then we can try to figure out what that distance is right there. The square root of that, yes. However, there's a little bit more to it because it's not a 90-degree angle. So the issue is, remember, we got to find this point, find their displacement, and then take the square root of that guy. Yeah, finding x for this point. Yeah, so you got to find x1, y1 here, then x2, y2. Have a good one. What? Yeah, you do 550 times cosine of 40 degrees, and then 550 times sine of 40 degrees.